Hello everyone, welcome to the post-contest discussion of Atcoder beginner contest. We will be discussing questions from A to F. So let's get started. So in question number A, what we are given is, we are given an integer n, and which is between 1 to 9, and we need to concatenate n copies of the digit n. So basically what the question means is, suppose we are given 3, then we need to make like 3, 3, 3. If we are given 5, then we need to make 5, 5, 5, 5, 5. So it is in simple code. Basically we first take a input and then we make the character, and n times we just basically keep adding it. Okay, one thing to notice for the beginners would be s plus equal to n, like s plus equal to c is much faster than s equal to s plus c. So that is something to keep in mind, though in this question it won't matter really. So yeah, that is all about question A, simple question. Moving on to question number B, what we are told is, we are given a pentagon. It is given and the vertices are numbered as A, B, C, D, E. Determine whether the length of line segment connecting S1 and S2 of P equals to length of the line segment connecting T1 and T2. So what we are given are like total 4 points: S1, S2, T1 and T2. We need to join like from S1 to S2 and T1 to T2, and we need to say if the length of these line segments are equal or not. So let's say our S1 is A and S2 is C, and T1 is B and T2 is E. So here what we can see is, like, if we join AC, so it consists of like a triangle, and yeah, and if we join B and E, so yeah, we can see that these two are of same length. Suppose let's say not these two, and let's do A B, like S1 S2 and T1 T2, T1 T2. So here also length is same. So how can we check that if the lengths are same or not? Since it is a regular pentagon, if the vertices, if the number of vertices between the given vertices are same, then it is then the lengths are same, because there are only two possible lengths possible: 1, 2, 3 and 4, and this is same, and this is same. So only two possible lengths is possible. So yeah, so at first we take the input, basically string A and B, where A0 is S1, A1 is S2, B0 is T1 and B1 is T2. And then we basically check their distances using like absolute of A0 minus A1, B0 minus B1. This ABS function, what it does is, if it is negative, basically a modulus function, it returns only positive integers. And we will check if dist is equal to dist1, basically simply distance is dist equal to dist1, or dist plus dist1 is equal to 5. Okay, why this case is coming? Because it can be like we are moving from D to D. So when we subtract, we will get this length, but we are not considering this. And if we take like A to C, then these two lengths. So, but these are equal, right? Because this and this. So how can we check that? To check that, we are doing this because we don't know the ordering. They haven't given if S1 is less than S2 or anything like that. Yeah. So that is all about B. And moving on to C. What C has told us is, a repunit is an integer whose digits are all 1 decimal representations. The repunits in ascending order are 1, 11, 100, 111, like that. So 1, 11, 111 and stuff like that. It goes on. Find the nth smallest integer that can be expressed as the sum of exactly 3 repunits. Okay, so let's see how it looks like. So our rep units are like 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, and so on. Suppose we are taking like these three. So 1, 1, 1, 1, 1, 1, and 1. So 3, 2, 1, 1, 1, 2, 3, stuff like that. So what we need to say is the nth smallest integer that can be expressed as the sum of exactly 3 rep units. Okay. Here our constraints are given that it goes exactly to 333. So one thing to notice is, Like how far can 333rd number can be? That is the question. We are given a test case which actually helps with this question a lot. I'll show you guys. So what we are given is here we are asked 333. This test case is given, which tells us that this is the output, like 1, 1, 2, some 2s and some 3s. So by this what we can check is till what Repunit number we'll need, like how big of a Repunit number we'll need. Do we need a 100-digit Repunit number or stuff like that? Since the biggest number can only be like of how many digits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 digits. So we will never need a Repunit number of like where it consists of 12 ones. We won't need that. We'll only need at max 11 ones. I hope that is clear. So what I did was initially store all of them in the vector, and since it is just of 12 size, so I can like basically create all the numbers which we can create by summing exactly 3 of them. So basically I did 3 for loops all till 12 and I inserted Vi, Vj and Vk. One thing to notice is if we directly sort and output that n-1 integer, it won't work because of course there will be duplicates. Like from here we can get 1, 11, again 1. We can get it in other ways also 1, 11, 1, 1. So there will be duplicates of course. So that's why what we can do is we will insert all of these in a set, and then we will again assign the whole set in the vector. By this we will get only unique numbers and sorted. Basically the set moves on to a vector. This line is quite useless here. So yeah, that will be my solution for question C. Following question D will be explained by Raj. Raj, you can continue.
Okay. Screen visible है क्या भैया?
Yes, it is visible.
Okay, so problem D, erase leaves. You are given a tree with n vertices, and vertices will be from 1 till n, and you will be given n-1 edges, where ui is connected to vi as well as vi is connected to ui. And this question is stating that consider the repeating flowing operation some number of times, like choosing any one leaf, let's say vertex v, and delete it along with all its incident edges. We will discuss this what this is stating. And we need to find the minimum number of operations required to delete the vertex 1. So let's just see one example over here. Let's say we have given a tree something like this. 1 is over here and some nodes over here. Over here, if you'll see, 1 is connected to this node, which is having 3 extra nodes. And 1 is also connected to this subtree, which is having 3 extra nodes. And 1 is connected to this subtree, which is having 3 extra nodes. So in order to delete a node 1, we either need to delete this node. Because this is the leaf node, we can delete it, or we can delete it this node and then this node and then this node and then this node and then this node, and finally we can delete 1, because after deleting this subtree and this subtree, our node I mean vertex 1 will be a leaf node, and then we can delete a node 1. So here the answer will be these 3 nodes plus these 3 nodes and extra 1 moves to delete this vertices 1. One thing to notice over here is we just need to find whatever the number of subtree 1 is having. Over here, the 1 is having just the subtree 2, and this is one of the subtree of 1. This is one of the subtree of 1, and one subtree is having 2 nodes, and another subtree is having 4 nodes. So what we can do is we just need to select. So let's say there were a subtree in a vertices 1. So we just need to select k-1 vertices of subtree of that node. So let's say over here, the total number of subtree was 2. So we just need to select any one subtree having minimum nodes. For this case, we will select this subtree and try to delete this node. And since deleting this subtree, we left out with one vertices to a leaf node, and then finally we can delete this leaf node. For an example, let's just take one more example. This is one. Say one node is over here, one node over here, one node over here. Thing like this. So what we can see over here is this is one subtree for an example. This is another subtree. This is another subtree, and this is another subtree, and this entire thing is one another subtree. Over here, the total number of nodes is 1, 2, 3, 4, 5, 6. Either we could delete this entire 6 and then this and then this and then this and so on, or we can delete this node, this node, this node, this node, this node. So over here, in order to do this, deleting this node will be 1, and deleting this entire thing will be 1, 2, and deleting this thing will be 1 and 1, 1 and 1, and deleting this will be 1, 2, 3, 4, 5, 6, 6. So in order to delete a vertices 1, we will sort this entire vertices, like sort this entire nodes each subtree we are having. So it will be 1, 1, 1, 2 and 6. We will not include 6 and will include these answers and sum it up. So 2, 1, 3, 2, 3, 4, 2, 1, 3, 4. So answer will be 5 because we can delete this node. This was a leaf node. After deleting this, this will be a leaf node. We can delete this node. For now, the answer is 2. We can delete this node 3. We can delete this node 4. We can delete this node 5. And since after deleting this node, we'll be just left out with this entire tree after deleting this node. And after doing this, so one will be left out with a leaf node. And we can finally delete one. We do not need to do operations on this subtree. So this will be just a simple approach to do this. And one thing also, what if initially the vertices 1 is itself a leaf node, then the operation will be just 1. Like consider this tree. In this case, 1 itself is a leaf node. So the number of operation to delete vertices 1 will be 1. That's it. We just need to calculate for each and every subtree 1 is connected to the number of nodes. We will store that, and after storing that, we'll sort the number of nodes each subtree were connected to that one, and we will take k minus 1, assuming k were total number of nodes that each subtree we are having, like total subtree we are having, and the code will be looking something like this. So this function, subtree function, will be basically to calculate the number of nodes in a subtree that one was connected to, and this is just the input part. And this is the subtree array we created. And this is the function call for subtree that will create a subtree for each and every node. And for node 1, I'm saying I'm just assuming that what nodes are there that are connected to node 1. For that, each and every node will connect. We will try to find the number of nodes that connected to over here. We were calculating this thing. Like 1 is connected to this node. So we will calculate how many nodes are connected to this node, including this node. So 1, 2, 3, 4, 5, 6. This is what we are counting over there. For each and every node, 1 is connected to, like if there was suppose this node, this node, this node, we had calculated for this node, this node, this node, and this node. So the array list would have storing 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, something like this. And after this, we will sort this and take k minus 1, where here k is 2. This is what we are doing over there. And we just find the I am just putting that subtree size, how many number of elements that each subtree we are having, and then we sort that result and take one less element that were present in that array, because we know that we just don't need to take that extra element, since one will be the vertex 1 at the end, the leaf node. And this is the base case, like if vertex 1 is itself a leaf node, the operation will be 1. Otherwise, the answer will be total number of nodes plus 1 to delete the vertices 1. I hope this is clear. Okay, भैया.
Okay, I'll move on to question number E and F. So yeah, let's move on to question number E. Let's read the question once. So Takahashi will embark on an adventure. During the adventure, n events will occur. Ith event is represented by a pair of integers ti, xi, and is as follows. So what if ti is equal to 1? It means that we get a portion of type xi, and we can choose it or not choose it. And if ti is equal to 2, we encounter a monster of type xi. If he has a portion of type xi, he can use 1 to defeat the monster. If he does not, he will be defeated. So what we have to say, we need to first determine whether we can defeat all monsters or not. Okay, and if we can defeat all of them, then we need to determine k such that that is a minimum number of potions we will carry at any moment. It is the maximum number of potions we will carry at any point of time, and that we need to minimize it. Okay, I'll explain the question a bit more. Yeah. So basically there is a monster. He has a type xi, and there is a potion. Potion also have types. So to kill a monster, we need a specific portion of xi type only. Okay, and we will be like throughout the queries, there are like stages. We can encounter a portion of type xi. We can encounter a monster of some xi, or like another portion, another monster, and stuff like that. Okay, let's denote the portions as P and monster is like, let's denote PI is basically portion of ith type, portion of ith type, and MI is monster of ith type. So the order of the what is it told? The order of the events, let's make it horizontal like this. So let's say these are like times or the number of events, stuff like that. So here suppose we get P2, here we get P3, here we get M2, here we get M3, here we get P3, and let's say another here. Here we get P2 another, and here we get monster 3. Okay. So let's suppose this is an example test case. So at first we get a portion of type 2. Okay, I'll take it. A portion of type 3, I'll take it. And there is a monster. I have a type 2 portion, so I can kill it. Then monster of type 3, I have a portion of type 3, so I can kill it. So here I get another portion of type 3. Okay, let's now not wonder about the minimum part. I'll take it. And then portion of type 2, yeah, I'll take it. Why not? And then monster 3. Do I have a portion of type 3? Yeah, I do have. So I can kill it off. So basically to check if we can kill it or not, what we need to check is at any point of time, like if do I have enough portions of that specific type I to kill off that monster I, right? So initially what we will do at first, we will check if we have enough portions or not. If we get enough portions or time or not. Enough portions or not. Okay, this we need to check. So let's parallelly see the code also. So for checking, what I have done is initially all the events I have stored in a vector act of I0 and act of I1, and this map is basically keeping the count of like portions we have, or like I have kept it as a standard that when we encounter a monster, then we will do plus plus, and if we encounter a portion, then we will do minus minus. Okay, so at any point of time for a specific type, this is basically giving me a type and comma net portions we need, something like that, net portion or net portion comma monster. So basically what this contains is, suppose MPP of x equal to 5. What this means is there are 5 monsters left to kill, monsters left. Suppose MPP of x is equal to -2. This means we have extra 2 portions. I hope this part is clear. So so what we are doing is basically act of I 0 is equal to 1. That means we can take portion. I'll come to the optimization part where we will minimize it, but let's not worry about it. Suppose we will take the whole thing. And MPP act of I 1, if type 2, then we have encountered a monster and then we are doing plus plus. Okay. So this is the checking part. What this is saying is if it dot second, basically that net monster or portion part is positive or not. If it is positive, that what does it mean? It means that monster has not been killed of that type I. In that case, if we are doing a -1. So after this point, we know that all monsters can be killed, right? So we did not worry about like if it can be killed or not. Okay. So next thing, now we have solved the first thing, if they can be defeated or not. Now next comes the minimization. Okay. Initially, since here it is like constant is 2 into 10 power 5. Initially we can get an idea of like DP sort of something, because there we can like pick a portion or not, or discard it. But since the n is 2 into 10 power 5, it will be hard to do so, like picking and not picking. We will have to keep a track of which portions we have in the states, which will be expensive. So we need to think something of greedy. Uh, Many of us can think of binary search also, but in binary search the predicate function will be quite difficult to write, I guess. Anyways, even if you go to write a predicate function, you'll get to say is there is a way of taking the portions. So the main intuition is like, if I have cleared all the monsters in the right, I wouldn't need to pick any portions now. What does it mean? So in this example, uh, let's see what does this means. Suppose I have M3. Oh, sorry. Suppose I have M3 here, M2 here, and like P2, P3, P2, and let's say something. Let's say M2 here. Yeah. So what we will do is we will check from this side, like how many monsters have we have encountered, and if we get a potion and there is a monster, we will take the potion. So we got M3, M2. We get a portion of P2 which can neutralize this, which will neutralize this. So yeah, this part is cool. Now M3, P3, yeah, this P3 can neutralize this. At this current stage, my MPP of 2 is equal to 0 and MPP of 3 is equal to 0. And now we encounter a portion of 2. Should we take it? No, we should not. Why? Because we have already killed off all the monsters in this part, right? So why would we need to take this potion? We need not, because this potion will not help us kill this monster. For this monster, we need a potion at this right only, not beyond. So that is the main idea, that if all the monsters have been killed of that specific type, we did not take that potion. If it hasn't been, then we will take that potion. Okay. So that's the main idea of this question, that we will iterate from the opposite side in a reverse order, and uh, if there is a monster, see, there is a monster. Basically, whenever my map of act I1, basically of that type, it is positive, means there is a monster. And then what we will do, we can neutralize it by taking a potion. And we will, acha, in this question, we also need to output that which portions we are taking and which are not. So for this, I am making an answer vector where we will be keeping like if I'm taking it or not. If there is a monster and we will take that portion, so I am pushing back 1. And if there is no monster, we will not be taking that portion, thus we will push back 0. And otherwise, we will just do, if we encounter a monster, we will increment that type. Since we are moving from the back, so we will need to reverse our array. And now we need to also output the maximum count we are taking during this duration. Okay. So how we will do so, we will again repeat the same code. This could have been merged, but yeah, there is a repetition of code. We will keep track of the number of portions we have, irrespective of the type. Let it be type 2, type 3, I don't care. So we will just uh, keep a count of the portions we have. So like suppose we get an portion and there is a monster, and yeah, I'm taking the portion and count plus plus, and If there is not, then count minus minus. And throughout the time I am keeping a count, maximum count, like like if at any moment it get maximized, we will store it in max count, and like I am outputting max count and printing the answers of which portions we have taken or not. I hope this is clear. So this was question E. So now let's move on to question F. Okay. In question F, let's see what it is given. There are n people standing in a line with person I standing in the ith position from the front. Repeat the following operation until there is only one person left in the line. Remove the person at the front of the line with a probability of 1 by 2, otherwise move them to the end. For each person 1 to n, find the probability that person I is the last person remaining in the line. Modulo 98 that mod stuff. Okay, and one thing to notice here is n is 3000. So we can aim for something like of n square or something. We can look for like that. Okay, I'll explain the question a bit. So there are basically n people. Let's say example 5, and they are initially standing in a line. Person I standing at the ith position from the front. Okay, let's for convenience, let's consider my front is at this side. Like imagine it is a line, queue line type or something. So what we are given is ith person is at ith position at the front. So basically 1, 2, 3, 4 and 5. So this is our initial, I'll call this a configuration or line. Let's say a config. So what can happen? Repeat the following operation until there is one person left in the line. Remove the person at the front of the line, basically him. There is a probability of half that there is like 50% chance this person will be removed. If we remove this person, what will happen? 2, 3, 4, 5. 2 will come at the front, 3, 4 and the order will be maintained. And there is another half probability that we will move 1 in the back. So what will happen? 1, 5, 4, 3, 2. So okay, we get two new configurations. This configuration is a new configuration of 4 size, and this is another configuration of 5 size only. So my idea is pretty much simple actually. So we will be solving it using DP. Okay, DPIJ. Two-state DP, I can be go to like 3000, even J can go to 3000, so we won't be having any memory problem. What does this say? DPIJ states that probability that jth person is the last man remaining when we started with high number of persons. What does it mean? What it means is, suppose DP 5, 3. Our initial configuration will look like something like this: 5, 4, 3, 2, 1. This will be our initial configuration, and this tree will tell us that this tree is the last man remaining. Okay, the concept of last man remaining would be like, suppose here it is went to like 5, 4, 3, 2. Then we remove 2. Suppose then we remove 3. Then we remove 4, and at last 5 is remaining. Or we can do something like this. In this case, we will remove 2, we will remove 3, we will remove 4, we will remove 5, and in this case, number 1 is remaining. Right. So we will be solving using this DP. So I hope the state is clear. Now let's move on to the transition. What type of transition it will go through? Okay. So we saw that from a configuration, there are only two possible configuration we can go to, right? This and this. And let's consider that we are solving for the one who is at the front, because yeah, he will only move. So the thing is, if you see, let's say he is in the first position, right? If I move it to like, if I remove him, there is zero probability that he will be the last man remaining because we already removed him, right? And if we move him to the back, this configuration is a new configuration, but it has a similar or equivalent configuration as our beginning configuration, where like 5, 4, 3, 2, 1. So let's consider for just a sec that we have already calculated the probability for each one of these. We have already calculated the probability of each one of these. So basically we know like the probability of the fifth person staying at the last. So what we see, if we know the probability of this fifth person staying at the last, here in this case, what is the probability of one staying in the last, or like one staying at last? That is same as probability of 5, right, in the initial configuration. Like this is something to understand. Basically, whenever one moved at the back, how much probability does it have to stay at the last? Okay, something to know is that what our probability of the person staying at last, what does it depends upon? It depends upon which position you are in from the start. That is my main parameter. Since one moved to the last, the probability of him staying at last is the same as probability of 5 staying at last. This is the main idea of the question. Okay. Now let's see, I guess for 1 it is understood. So let's see for 2, 5, 4, 3, 2, 1. For 2 to be the last person remaining, let's minimize it. For 2 to be the last person remaining, what can happen? First and foremost thing is, there is two things we can do. We can remove one or we can keep one. So like let's say we are removing one, 5, 4, 3, 2, and let's say we are moving one to the back, 5, 4, 3, 2. Okay, so for 2 there are again two configurations arising. One configuration is 2 becomes at the front, and another configuration is 2 comes at the front, but there are total 5. Okay, so suppose we know the answers of everything, know the probabilities of everything. Isn't this equivalent to 4, 3, 2, 1? This is equivalent, right? Probability of these two staying at the last is same as the probability of this one staying at the last. What is this? This is dp 4, 1. And similarly, 1, 5, 4, 3, 2, 1, when we move it to the back, the probability of this two staying at the last is same as dp of 5, 1. I hope this is clear, like the fact that these are equivalent. So by this what we get is several equations. I'll show the equations. So let's consider a case for there are n equal to 3. Okay, dp 3, 1, dp 3, 1, what does it mean? 3, 2, 1, probability of 1 staying at last. What can one do? What one can be removed, 3, 2, or one can be moved to the back. If we remove it, there is a 0 probability chance, so half. So half into 0 probability plus we move here half into, here 1 is the position of 3, right? 3 to 1 in our initial config, that is the position of 3. So the probability of 3 staying at the last will be the probability of 1 staying at the last in this configuration after half probability. So half into dp 3, 3. Okay, this is understood. Next we move on to dp3, 2. dp3, 2. So there is again two probability. What does it mean? Initially we are at 3, 2, 1. There are two configurations like 3, 2 or 1, 3, 2. Okay, so these are two configurations, both equiprobable, half half. So for this, yeah, here 2 is there. So what is the probability of this 2 remaining at the last? That is half into dp of 2, since there are two elements. So this is equivalent to 2, 1. and it is in the position of 1. So 1 plus half into, here if you see 1 to she, sorry, she to 1. Here 2 is taking the position of 1 again, and and 2 is taking the position of 1. Thus, the probability of 1 staying at last is dp she 1. I hope these equations are clear. Next, lastly, dp she. What does it mean? She to 1. She is the last man standing. So this can move to two configurations, she 2 or 1 she 2. Okay. So what is this? This is equivalent to 2 1 at the position of 1. So half into dp 2 2 because it is in the position of 2, and we already suppose we know the values of these, plus half into, and in this case 3 is coming, like it is equivalent to the config of 3 2 1. So 3 is coming at a position of 2. So thus half into dp 3 2. Okay. I hope how I deduce these relations is pretty much clear. So now we have 3 equations, and let's consider that since we are like evaluating it through dp, let's consider that for every j less than 3, that means for 1 comma 2, we already know the value of dp2s, like dp, we know the value of dp2 3 2 1, dp 1 0 and stuff like that. We already know the values. So how many variables do we have here? Like how many variables do we have here? This is an variable, this is an variable, this is an variable, this is also an this is the same variable, and here also the variable, same variable, and here also, yeah, this is also same variable. So we have 3 variables and we have 3 equations. So what we know is that, like, if we have n equations and n variables, we can solve it. So by these 3 equations, we can easily get the values of these variables, correct? So how to do so basically? Now in the code, if we go to solve them using any mathematical approach, it will take time. Basically, it will take approximately, I guess, n square time. So for these only n square, and then again iterating for till come to chi again n, so that will get into n cube complexity, which we don't want. We need to optimize it. So we can do some mathematical optimizations here. So how to do so? Let's remove this part because this is a 0 part. How to do so? So what we can see here is this equation. We can substitute this part here, and then we can substitute this part here. So there is forming a chain. So what happens if we substitute the first substitution, dp2? It becomes half into dp21 21 plus half into dp31 is half into dp3. So this becomes 1 by 4, and yeah, and dp33 becomes half into dp22 plus half into this whole part. So basically, let's move this to the side. Half into half dp21 will be 1 by 4 dp21 plus half into 1 by 4 is 1 by 8 dp33. And see dp33 dp33, and these two values we know. So by this we can calculate the values of dp33. What is dp33? dp33 becomes we move 1 by 8 here, so we get 7 by 8 here, and then we move 7 by 8 to that side, so we get 8 by 7 into half into dp22 plus 1 by 4 into dp21. Okay, so from this we basically get a formula dp33. For dp33 we can calculate, we get a formula for to calculate this. So okay, so moving to the next part, what will be the base condition? We know if there is only one element remaining, Suppose only 1 is there. He is the last man standing no matter what, and thus he has a probability 1. So we know dp11 is 1, and from dp2 we need to calculate. dp2 we need to calculate. Okay, so now we have reduced a formula. Let's write it. dpii. There is a formula here. What is the formula? Ignore the constant part, or maybe not. That is basically 2 power I divided by 2 power I minus 1 multiplied by, there is a summation there. Summation, it will be basically till j less than I, basically, then dp I minus 1, dp I minus 1, and then 2 1, yeah, so j, and multiplied by 1 by 2 power, since here I guess 2 power n minus j will come, I guess, sorry, I minus j, yeah. So this is my formula. Using this formula we can easily calculate dpii, and when we calculate dpii, like in this case, after we have calculated dpcc, we can put the value of dpcc here and get dp1. We can use this dp1 and put this here to get dp2, and we can go on like that. So let's, I hope the basic idea is clear for this question. So since we are we have to take mod again and again, I am here using modular int mint and creating an vector of size 3000 into 3000. My base condition is 0, 1. Since everything I am keeping is 1 based indexing, so I am keeping a 0 at the start. This can be ignored, no need. Moving to this part, we will start from 2. Since we know the 1, we know for dp1, this is our base condition. We will start from 2. So what we need? Initially, we will try to calculate this dpii part. How we are calculating dpii? So yeah, this formula 2 power I, we will do this later. This dp I minus 1 j divided by 2 power I minus j. So what we will do is, since see what we are doing here is like there is a 1 by 2, then okay, this should be 1 by 4. This should be 1 by 4. This is a 1 by 4. If we had more values, that will be 1 by 8, dp something, no, 1 by 16, stuff like that. So 1 by 2, 1 by 4, 1 by 8, it is a moving on. So I am taking an factor. Basically this is a part we are multiplying. So initially it is fc as a value of 1 by 2. So what we do, fc multiplied by dp I minus 1 j. We are moving in reverse from I minus 1 to 1. And we divided by factor 1 by 2, so that we get 1 by 4, and then we keep adding, since this is in summation. So at last we get the dot. So our total is basically dpii, okay. And then since we need to do this 8 by 7, 2 power I divided by 2 power I minus 1, we can actually do this in this way. 1 minus 1 by 2 power I, this gives us 2 power I minus 1 divided by 2 power I, and then just reciprocal of this. So that's what I am doing. Initially I am subtracting 1 minus fc. Okay, the factor will move to 1 divided by 2 power I directly instead of calculating, because I am dividing by 2 after the operation, and we am reciprocating this, and then at last I am multiplying it by total to find my dpii value. So we have this value, right? Now we need to calculate the further values. How to do so? Okay, there is a fixed thing that whatever dp1, basically dpi1 is half of dpii. That is also one more formula we will need. That is dpi1 is equal to half of dpii. So we use it here in this place. dpi1 is equal to tot by 2. Tot is basically dpii, and we will again move from 2 to I, and we just keep passing the value using a pref. We are keeping pref as dpi1, and initially we are doing pref by 2 plus dp I minus 1 j minus 1 divided by 2, and I am storing it in the dpij and then keeping track of the pref, and through this we can get the probabilities of ith of jth person staying at the last. I hope these questions are clear. If any doubts, then you can ask. So I guess we can wrap this up. Thank you for joining in.